Fischer esterification is a fundamental esterification reaction, usually learned in organic chemistry too. And what it is, you take a catalytic amount of acid, usually a strong acid like sulfuric acid, and then you take a carboxylic acid and an alcohol, and you create the corresponding ester. Now, just remember, an ester is a carboxylic acid derivative with an alkyl chain on the other side of the oxygen there. Now, this is one that they usually teach in organic chemistry lab to teach you about the sense of esters and kind of like perfume chemistry, for lack of a better term. It's one that students really enjoy. You can do it in test tubes. It's pretty easy because acids are generally like kind of nasty smelling and higher boiling points, so they're not typically as volatile. However, esters, because we lose that functionality here to hydrogen bond, are much lower boiling point, more volatile typically. And this is actually kind of what is in perfumes. It gives them their scent. And these are usually sweet or fruity smelling. So it's a really interesting lab for students. If you have that in your organic chemistry 2 lab, that's going to be a fun lab for you. But what is the mechanism for this? Let's go through this right now. We're just using R1 and R2 as our stand-ins, but you just plug and play with your carboxylic acid and your alcohol. There's a lot of different combinations you can make. It's really interesting. So the first thing we're going to do here, remember we have a catalytic amount of acid. This is, remember I said usually sulfuric acid, H2SO4. I'm just going to use H plus for the purposes of this. And if you get confused as to where H plus comes from or ever H3O plus, go review your acids and bases. Okay, that's a good spot because in organic chemistry, usually we just say H plus cat or H3O plus, and so we're going to protonate our carbonyl first. That's the first thing that happens. So we come down here and we have our carbonyl is now protonated on that oxygen, meaning the oxygen has a positive charge, and the oxygen absolutely does not like that in the slightest. And now, let me fix that. Remember that the carbons in a carbonyl are generally very primed for nucleophilic attack, except for carboxylic acids. But now, because we did this is pulling all this extra electron density up even more, and it is primed for that attack. And so what happens is then our alcohol comes in and attacks that, and we're going to kick these electrons on up. And this is what happens when we get to this here, where we have this tetrahedral intermediate, where we have an alcohol, not an F, and now we have OH plus, and then our R2. And now this is where the parts get a little confusing for some people because there's a lot of moving pieces. Now it's important to remember, if we could differentiate these, that the original alcohol is actually that oxygen. Go on now, get. So what happens is there is a proton transfer here where this gets taken and these electrons move here. So now we have OH, OH2 plus, R2, R1, and these are like, all right, we're just gonna go on now and leave. And then we're gonna have these electrons flow back down here, and we are going to create this species right here, where we have a protonated carbonyl again, which remember is not happy in the fucking slightest. But now we have our ester formed there. And then you can take another Wooder, come and steal that, donate our electrons back, which gives us our ester. And then we also regenerated our acid catalyst. Remember, this is just catalytic acid. H2O plus, it doesn't need the circle. So that is what that looks like. So a lot of times what you'll be asked on your exams, we'll go over some examples here where we don't work through the mechanism. So say we want to make ethyl acetate. Okay, this is what ethyl acetate looks like. It's a terrible oxygen. So what do we need for that? We need go like this. We're like, okay, so we need that's acetic acid. Then we go this way. What do we need? All right, we need that's well ethanol. So you take acetic acid plus ethanol, and H plus cat. Usually in real life you do a little bit of heat, and that gets you your ethyl acetate. Now we can go the other way. Say we have propanoic acid. We have methyl propyl. All right, and we have say 2-propanol. Well, what does that give us? What I do is you can draw your carboxylic acid. I'm going to flip it though for this case. Draw your oxygen, leave off the proton. And what do we have here? We have 2-propanol. And this is, so we would have, I guess this is isopropyl. So we would have isopropyl propionate. So that is how you do your Fischer esterification. It's really not that hard. Once you learn it, it's remember you're just essentially shoving an alcohol and an acid together where their OHs are, and then you lose water in the process. And that's what it is. Just you combine them, and then if you have to go the other way, just piece them out. Now, an important thing to remember is this mechanism is in equilibrium, because when you'll learn that the same conditions for a Fischer esterification are also for an acid catalyzed hydrolysis. So there is some back and forth. Those mechanisms we work through, those are all double arrows. They go both ways. So just keep that in mind. And for more organic chemistry learning, hit that follow button.